Next talk, Dr. Qureshi will talk about surface technology only or 3D printing.
All right, thanks, Dan. Appreciate it, and thanks to Solus, to Ron and Brian for having me here. So I'm going to talk about surface technology and 3D printing, and probably, the best differentiator here. I think surface technology and 3D printing can be a little confusing. It really should be surface technology versus fully porous technology, because 3D printing can imply surface technology. So just sort of keep that in mind as we go through the talk. I just wanted to thank Stryker and Nuvasive for providing me with a lot of the slides that you're going to see here. So, as you just heard Steve talk about, there has been an evolution in terms of interbody implants, starting with titanium interbody implants, or stainless steel, interbody implants, moving to titanium, sort of solid blocks, thinking about PEEK, and then ultimately moving towards more 3D fully porous technology, as you can see here. So, we had heard about sort of where this all comes from. I mean, initially, several years ago, we were really thinking about PEEK or titanium. Metals were popular, plastics became popular, metals are popular again. And basically, the reason behind this is that while clinically and radiographically fusion rates are relatively similar, there are greater subsidence risks with titanium, perhaps lower collapse risks, though, with titanium or PEEK compared to bone graft. And so there is sort of this constant thought around how can we make our fusions more predictable. So in terms of surface technology, I think a lot of implants have been investigated, and titanium alloys are probably the most common. And you want to think about this sort of as trying to create a rougher surface, which increases that integration between the implant and the bone, and allows for not only a better pull-out strength, but then also creating an environment where the bone is going to want to grow onto the interbody implant that we've placed. And sort of when we think about the technology behind surface design, there's that implant material, so you can have whatever the implant material is that you're going to use, and then ultimately the surface treatment, which is often some sort of a titanium that's going to be placed there through a variety of different techniques, whether it be blasting or micro etching, but really just placing a surface that is going to be important for that for the bone implant interface to allow for integration. And there's a lot of different modalities that can be done through. So when we think about nanoscale surface technology, I think we heard a little bit about that. So there are certain cages that are really relying on that surface to be to have a certain type of pore and a certain type of etching along that surface that's going to that is going to allow the bone to provide progenitor cells really at a molecular level to be able to create a better surface environment. So what's the current state of surface technology? I think, surface technology has certainly shown to reliably facilitate fusion. I think it's going to continue to grow as a part of what we do. And I think that there are obviously certainly opportunities to explore this. So what about manipulating the implant surface? So implants generally are created through a coating process, and cages of all different types of materials can be plasma sprayed with titanium alloys. So this is sort of a common when we think about surface technology. Oftentimes PEEK is used as the core material and then can be coated with a titanium. And the thought behind this is that by doing this, that you're sort of taking advantage of the lower risk of subsidence with PEEK, but still allowing for that benefit of bone integration that happens with metals. And then as I talked about, sort of in the beginning here, you can combine 3D printing with surface coating. So 3D printing doesn't in and of itself mean that you're dealing with a fully porous implant, that you could still be just dealing with what we would consider surface technology. So what are the manufacturing process differences here? There's sort of surface technology and 3D printing, obviously they have the same goal, right? The goal is to try to use the implant to enhance fusion, but they're often done in different methods. Subtractive manufacturing, essentially you've got a block and you're cutting things away. Additive manufacturing, which is really what 3D printing is, Most of what surface technology is where you're placing something onto an existing block, or where you're actually creating something from different layers, and I'll have a little cartoon of that. So in terms of sort of what kind of 3D printing we have, I think the most common ones, the reasons, that the ones that I'll show here from both Stryker and NuVasive, I think are probably the most common ones used when we're thinking about either T-lift surgery or X-lift surgery. And these are all three-dimensional products or 3D printed products, and they're fully porous. And again, we just heard a really nice talk from Steve regarding the importance of pores, and sort of the goal here being is to try to mimic that perfect pore size, amount of porosity, and how they interconnect. Can be very important. Now, the Stryker technology specifically, is sort of around this laser rapid manufacturing. That's really less important. I think really the thought here is, why are we moving towards this? When we think about, obviously there's a cost that's likely being added to using cages that are printed in a certain way, or that bring this in, and sort of is using these cages worth the additive cost? So when we think about surface technology, it does improve osseointegration, but probably the fully porous technology really not only improves that, but allows for manipulation of the mechanical properties, and then maybe help with imaging artifacts. So this is similar, I think, to a slide that we just saw, but really just showing that sort of smooth peak probably isn't what we should be comparing to, because I think we'd all agree that with smooth peak, there's really not going to be anything happening at the surface here, and things are going to have to grow through. And solid materials that have this surface technology either etched or blasted onto them can allow for on-growth, which is a sort of additive benefit compared to smooth peak. And then ultimately, if you can have ingrowth through fully porous materials, I think that's where 3D printing will have that advantage, because you'll have this sort of fully porous material and have a higher level of ingrowth here. So this is obviously, from a company, so take that as you may, but what you can see here is that compared to peak and sort of surface technology, if you do have fully porous technology, as is shown in sort of the third cartoon here, both 8 and 16 weeks, you can see sort of further growth all the way through. And when we think about the cellular response, certainly with 3D porosity, you can see that just sort of you have a response beyond the nanostructure. We had heard a little bit about the modulus of elasticity that Bob had shown. And so one of the nice things with 3D architecture is that you can try to control some of that modulus of elasticity to sort of fall right where you want it to. So here we can see that porous titanium, you can really manipulate it to fall right between cancellous and cortical bone. And perhaps even better than solid peak. There's been some thoughts around novel titanium and peak combined spinal fusion cages, which have had some good early things. But none of these things come without problems. So when it comes to surface technology, certainly there have been some reports on these implants failing in terms of the surface itself. And then also when it comes to 3D printed titanium, there have been some reports perhaps of cage fractures. But ultimately, I think that all of these things are going to help. And I think that similar to all technology, ultimately the goal is to create a fusion. This is just an example of sort of the different processes that happen to create a 3D implant. But I think what's important as a take-home here is that what was previously unmanufacturable now becomes manufacturable, and it can be rapidly manufacturable. So I think just in closing here, what we see from sort of the research is that what 3D printing really allows is that it allows us to create a metal that really mimics bone in terms of the pores. So just like Steve had just talked about, those pores become very important. And ultimately what that allows is an implant that you can create that'll have pores where you want it to, but also be safe where you want it to as we're passing these implants around neurologic structures, and then you can hopefully get a sort of solid fusion. This is just an example of an image of a CT scan showing sort of a surface technology at the bottom and sort of the bone kind of growing through a smaller area, whereas at the top here there's a 3D printed cage that's a little more porous and allowed to have a larger bone window. Thank you.